All right, so we're going to look at the final conic section that we're going to examine, and that conic section is the conic section of a hyperbola. So the equations for the conic section of a hyperbola look like the following. So the standard equations are either going to be x squared minus h squared, x minus h quantity squared divided by a squared minus y minus k squared divided by b squared equals 1. Or we switch and say the y minus k squared over a squared minus x minus h squared over b squared equals 1. So what I'm going to be often referring to is the positive component and the negative component. The positive component is the one I'm going to be calling this, where obviously a squared has to be a positive number, and we have a positive coefficient outside of our, in this case, x minus h squared, or in this case, we have a positive component of y minus k squared over a squared. The negative component is going to be the one that we're subtracting. So when I talk about hyperbolas and I say, well, the positive component versus the negative component, positive is the one obviously with positive coefficients. The negative is the one which has a negative coefficient because we're subtracting. Notice that the equations look very similar to the equations of the ellipse, but instead of adding, we're subtracting the two terms. All right, so instead of having both be positive, we're having one be positive and one be negative. Now, let me, we'll graph this in a moment, but let me talk about some of the properties of a hyperbola. So first off, the center of the hyperbola is at HK. I'm sure you've thought that that was going to be the case. The vertices are going to be A units from the center. Now, A units, if you notice these two equations, both had A underneath the positive component of those equations. And so when we say A units from the center, we're going to talk about A units in the x direction if the positive component has x's in it. And we're going to talk about the moving A in the y direction if the positive component has y's in it. All right. The same thing with the foci. There's C units from the center, and it's always whatever the X or Y is a piece of the positive component. If X is a piece of the positive component, then the foci is going to move in the X direction from the center, and vice versa if it is a piece of, if Y is a piece of the positive component. Now we're going to have a different equation for finding the C than we did with the ellipse. With the ellipse, we'd had a squared minus b squared. Well, we're not guaranteed to have the a be actually bigger than the b, so we're going to have c squared is equal to a squared plus b squared in this case. Now, there's some other things that we're going to deal with as well. We're going to have asymptotes with hyperbolas, b over a or a over b, depending on which type of hyperbola we have, positive or negative, depending on whether my positive component is dealing in the x's or in the y's. And then the eccentricity is going to be c over a once again. Now, by the way, interestingly enough, this c squared, since a squared plus b squared has to be equal to c squared, c has to be bigger than a with a hyperbola. So because we have a different way to calculate c, c is always going to be bigger than a. So my eccentricity is always going to be bigger than 1. All right, so let me talk about graphically what this hyperbola is doing. All right, so here's what I've done. I have graphed a basic hyperbola, x minus 0 squared over 16 minus y minus 0 squared over 25 equals 1. And so what's happening in this situation on the green is what I've graphed. All right. So what this hyperbola does is it kind of gives you two pieces which curve in, almost touch at a point. And if you zoom real close into them, they almost look like two parabolas going this way. But when you zoom out a little bit, what they look like is almost like they're straight lines, like they're coming out to straight line and then curving in and then going out to another straight line. Now that's actually on purpose, and that's what the things we call asymptotes are all about. So these asymptotes are lines that are hyperbola approaches. And you'll notice that under the X, I have 16. So that meant that the A was 4. Under the Y part, I had 25. That meant the B was 5. So if I talk about X's as 4s or negative 4s, and the Y's as 5 or negative 5, I can think about taking and creating the point 4, 5, the point 4, negative 5, the point negative 4, negative 5, the point negative 4, positive 5. And if we actually graph, connect these diagonals, so the point 4, 5 and the point negative 4, negative 5, and if we connect the point negative 4, 5 and the point 4, negative 5, it turns out those two lines that we create will be asymptotes. Now, let me just say those lines, we go 5/4 times x and y equals negative 5/4 times x. Let me change the colors on those. Let me make sure that these are blue in color. So these blue lines here give me asymptotes to my hyperbola. And if you scroll out, you'll see that these blue lines, as we get further and further out, look like they're really getting really close to I should say the hyperbola gets really close to these blue lines. All right, so that's what those asymptotes are all about. And you can see those asymptotes basically come out of our a squared and our b squared numbers. Now the other parts of the graph, other than the asymptotes, are the vertices and the foci. So the vertices are going to be these 2 points here. In this case, since 16 is under the x part, we're going to go negative 4, 0 and 4, 0. Those are our two vertices. So they're the sort of leftmost point on this part of the hyperbola and the rightmost point on this part of the hyperbola. Obviously, in this case, I've had my x as my positive component has involved my x, and my negative component has involved my y. If I were to have switched that, then all of this graph would be rotated 90 degrees, and your hyperbolas would be pointing up and down instead of left and right. So we go negative 4, 0, 4, 0 are my vertices. My foci, well, my foci are at, if you calculate this, it's like the square root of 41. So it comes out to about negative 6.40 and a positive 6.40. Now, the interesting thing about hyperbolas, and hopefully we'll be able to see this, is that geometrically, when you take a point on the graph, all right, so we take a point, an arbitrary point right here on this graph, and I look at these two lines. So from this focus to the point, and from this point to the focus. Now, obviously, as you change these, the sum of the two lengths are going to vary. Obviously, this sum of these two lengths has to be more than this because obviously a triangle versus a straight line situation. But what it turns out is the interesting thing is that if you take this length here, the longer one, and then subtract the shorter one, and then you move that point to another spot. Let's say we move it to here. And then you take the longer length and then subtract the shorter length. That difference would be a fixed number. So it would give you a fixed constant number. So whichever way you subtracted. And that doesn't matter whether the point is on the left-hand side, whether the point is on the right-hand side. The longer length minus the shorter length, again, is going to give me a fixed constant. So there you go. That's the idea about hyperbolas. So now let's do a couple of problems with hyperbolas. The first problem says find the center, foci, vertices, and eccentricity of this hyperbola. Go ahead and push pause on the video and do that. All right, hopefully you did that. So center, x minus 5 means my center has to have x value of 5, y plus 3, my center has to have a y value of negative 3. Now, notice that the positive component contains the y piece. Therefore, we're going to be adding and subtracting to the y value of the center to get our foci and our vertices. Now, you'll notice that the value underneath the y is 225, and therefore that we're going to be adding and subtracting 15 to the y value of the center to get our vertices. So minus 3, if I add 15, I get to a 12. If I subtract 15, I get to a minus 18. So my vertices are at 5, 12, and 5, negative 18. The foci, well, that's going to require us to calculate the c. And remember, in hyperbolas, we have c squared equals a squared plus b squared. Now, in this formula, the a squared and the b squared are kind of interchangeable, but it doesn't hurt to make sure that we always have it right. But we're adding 225 and 64 to get a c squared. Now 225 plus 64 gives me 289. If I take the square root of 289, I end up with 17. So, oops, c squared equals 289, so c is equal to 17. By the way, these few, a lot of times on the examples we do in class, they come out to a nice number, but don't get discouraged if your c squared comes out to something that's not a perfect square. So if your c is, for instance, the square root of 5 or the square root of 90, something like that, it's perfectly all right. So what that tells me is that in order to get to my foci, I need to add 17 to the y value of the center of the hyperbola. So if I add 17, negative 3 plus 17 is 14. If I subtract 17, I end up with a negative 20. So my foci are exactly what I stated there, 5, 14 and 5, negative 20. Vertices 5, 12, 5, negative 18. Eccentricity is C over A. In my case, that's 17 over 15. Okay, and notice 17 over 15, while that's not greatly bigger than 1, it is bigger than 1, 1.13 repeating in fact. So 1 and 2/15, if we want to call it mixed number. But it's bigger than 1. That's my whole point. So there you go. Now we found the center, the foci, the vertices, the eccentricity. If we wanted to find the asymptotes, we could. I'm not going to ask you to find the asymptotes of a hyperbola in general. So hopefully you see that. Obviously, things could get more difficult if you had to complete the square and you had to algebraically manipulate in order to get to the standard form. But in this case, we did not have to. The next question asks you to find the equation of the hyperbola with vertices 2, 3 and 2, -3, and having a point on the hyperbola of 0, 5. That's a method we haven't done so far, so that's going to be an interesting one. Push pause, try to think through how you would end up with vertices of 2, 3 and 2, -3, and a point on the graph of 0, 5. All right, so hopefully you went ahead and did that. Now the vertices being 2, 3 and 2, -3, we know that the two vertices of a hyperbola have to have the property that halfway in between there is the center. So the midpoint between two vertices of the hyperbola has to be the center, and therefore halfway between 2, 3 and 2, -3, we know that the center is the point 2, 0. Now, we also know that because in order to get to the vertices, we have to add the value of A and subtract the value of A from the center. We know that the value of A is 3. So that all came from the vertices point, that the center has to be 2, 0, and the value of A has to be 3 because the value of A has to be the distance, in this case, between the y value of 0 and the y value of 3. All right. Hopefully that all made sense. By the way, notice that I wrote my equation with the positive component having y values in it because that is the number that's changing from the center. So obviously we went from 0 to 3 to get to my vertex in the y value position. Therefore, the positive component has to have y values in there, and the negative component would have the x values. All right, so what we have so far is we have a center and a value of a. So y minus 0, x minus 2, and then we have a value of a is 3. So let's replace that a with a 3. That 3 squared is 9. I'll just call that 9. Okay, so we have y squared over 9 minus x minus 2 squared over b squared equals 1. And all we need to do is find b. Now here's where this point on the graph comes into play. I know that this equation is an equation for all points on my graph. Therefore, if I were to have plugged in the point 0, 5 into this equation, I should be able to get a true statement. So let's go ahead and plug in the point 0, 5 into that equation. 0 for the x value, 5 for the y value. Well, now I have an equation, and the only variable that's there to solve for is b, or in this case particular, b squared. So I can just take this equation and solve it for b squared. So I have here 25 over 9, 5 squared is 25 over 9, minus negative 2 squared is 4 over b squared equals 1. If I add, excuse me, what should I do? I should what do I want to do first? I don't know if I go left or right. Well, let's do this. Let's add 4 over b squared to both sides, and then I'll subtract 1 from both sides. So this is what I'll get. I'll have 25 over 9 minus 1 is equal to 4 over b squared. Okay? 25 over 9 minus 1. So take 25 minus 9. You get 16 ninths as that fraction. So the left-hand side simplifies to 16 ninths equals 4 over b squared. You can cross multiply, figure out those types of things. B squared would have to have been 4 times 9 over 16. However you'd like to write that, 4 times 9 over 16 like that, or like I had it before. So 4 times 9 is 36 over 16. Which, as a simplified fraction, gives you, I believe, 9/4. So b squared should be 9/4. Now that's a long way to do this, but that's, again, I'm trying to solve this. What I know now is that my equation should look like this, where b squared is 9/4. So we can just write 9/4, or the decimal version of 9/4, which is 2.25. And there you go. So that's the equation of the hyperbola that we were looking for. Now, the last example on hyperbolas, finding hyperbolas, I want you to try. Find the equation of the hyperbola with center at 0, 0, a vertex at 0, 2, and a focus at 0, 4. Go ahead and push pause and find that equation. All right, this one is a little bit quicker. Now we're going to use the same equation, specifically the one where the y component is the positive one, because in order to move from the center to the vertex, we're changing in y, and in order to move from the center to the focus, we're changing the value of y. Now here's what we know. We know the center is 0, 0. So that'll tell me what the h, k is. Both are 0. The vertex being 0, 2 tells me that the value of a in this situation is 2, because that's how many units I moved my y value to get from the center to the vertex. So a has to have a value of 2. Now the focus being 0, 4 tells me that my value of c, again c being the how many units I move from the center to get to the focus, has to be 4, going from 0 to 4 in the y value. C has to be 4. So I know the value of a is 2, the value of c is 4. That allows me to find the value of b using the hyperbola equation for finding the relationship between a, b, and c. The hyperbola equation, remember, c squared equals a squared plus b squared. So I just said c is 4, so c squared is 16. I said a is 2, so a squared is 4. B I don't know yet, but I can solve this real simple equation and say, well, b squared has to be 12. So I get this formula. I have all I need to know, or all I need right now. Center at 0, 0 means y minus k will be y minus 0. X minus h will be x minus 0. B squared I just said is 12. By the way, be careful you say b squared is 12. B is the square root of 12. And then a squared, be careful you put a squared, that's 4, not 2, right? A is 2, A squared is 4. B is square root of 12, B squared is 12. So that's the equation of the hyperbola you would get with center at 0, 0, vertex at 0, 2, and focus at 0, 4. So there you go. That is how we look at hyperbolas in this section.